Okay, so let's go back to our problem. So we had this problem of infinities. On one limit, we have the logarithm of 0, which is minus infinity. On the other limit, we have the logarithm of, well, when theta is equal to pi, cosine pi over 2 is 0. So we have the logarithm of infinite, which is plus infinite. So in any case, we ended up having an infinite vector potential. And we also said that, well, we had that same infinity in electrostatics, because in electrostatics, if you remember, if we set the vector potential, the static potential at infinity to 0, in that case, the electrostatic potential at everywhere is infinite. Now let's do something else. We will be, to get rid of that infinity, instead of having the vector potential, the total vector potential, let's calculate the vector potential. This is the point at which we are trying to evaluate the vector potential. Let's take a length L. So this is L over 2. This is L over 2. Instead of summing over all the wire, let's just integrate over this finite length. Well, when we are integrating over this finite length to get the vector potential of this infinite wire, the only thing we need to do is just take the limit L is equal to infinity. And then we will be done. Now let's define these angles. So this angle, let's call it theta 1. This angle is theta 2. Well, since I have chosen these segments to be symmetrical, this angle over here is basically theta 1. Then when you go back to this expression over here, the limits are not from pi to 0, but the limits are from theta 1 to theta 2. I just consider this finite segment. The contribution to the vector potential from that segment only. AZ, let's say partial, will be equal to, well, everything we did is basically the same. This is 8 pi. The only difference being theta goes from theta 1 to theta 2. Do you agree? So this will be equal to mu 0 over 4 pi I times the logarithm of tangent theta 2 over 2 minus logarithm of tangent theta 1 over 2. Now you see theta 1 plus theta 2 is equal to pi, or theta 1 over 2 plus theta 2 over 2 is pi over 2. So we have these two angles, and we are taking their tangents. So how are their tangents related? Tangent theta 1 over 2 will be equal to 1 over tangent theta 2 over 2. Because we have these two angles whose sum is 90 degrees, so the sine of one is equal to the cosine of the other one. So if you just exchange sine and cosine, you get 1 over tangent. So we don't need to. And since the logarithm of 1 over something is minus itself, so these two terms are basically, they contribute the same. So the result will be equal to AZ partial, so here I have a minus sign, will be equal to mu 0 over 4 pi I times logarithm of twice I logarithm of tangent theta 2 over 2. Now, what is tangent theta 2? Remember, this angle over here is theta 2. Tangent theta 2 over 2, we have to calculate that one. Well, let's see. Cosine of theta 2, which will be equal to L over 2 divided by L over 2 plus d squared under the square root. Now, L over 2 squared. Now, this is r. This is my cosine theta 2. But cosine theta 2 is equal to twice cosine squared theta 2 over 2 minus 1 and also 1 minus twice sine squared theta 2 over 2. Now let me write it properly. Cosine theta 2 is L over 2 divided by L over 2 squared plus r squared, everything under the square root. So cosine squared theta 2 over 2, this is equal to 1 over 2, 1 plus L over 2 divided by L over 2 squared plus r squared, everything under the square root. And sine squared theta 2 over 2, this is equal to, again, 1 over 2, 1 minus L over 2 over L over 2 squared plus r squared under the square root. So tangent squared theta 2 over 2, just take the ratio, and if you take the ratio, you would get L over 2 squared plus r squared under the square root minus L over 2 divided by square root of L over 2 squared plus r squared plus L over 2. This is my tangent squared theta.
Trigonometrik fonksiyonlar çıkardınız hocam.
Well, that's what we need, no? Now let's go back. AZ partial. It is partial because it's not the total vector potential, but the contribution to the vector potential from a segment of the wire of length L. To obtain the total vector potential, I will need to take the L goes to infinity limit, eventually. So this will be equal to minus mu 0 over 4 pi 2I logarithm of tangent theta over theta 2 over 2, which is equal to minus mu 0 over 4 pi I logarithm of tangent squared theta 2 over 2. Twice the logarithm of something is nothing but the logarithm of that something squared. So that's why I didn't take the square root of tangent squared. I don't really need it. And so AZ partial is equal to minus mu 0 over 4 pi I times the logarithm of square root of L over 2 squared plus r squared minus L over 2 divided by L over 2 squared plus r squared plus L over 2. Well, up to this point, not much improvement. You see, basically, if you take the limit L goes to infinity, this just becomes infinite. This becomes 0. 0 over infinite is, well, this ratio will become, if you take the L equal, this should become 0. 0 over infinite is just 0. Logarithm of 0 is infinite. So we didn't really resolve anything yet. But let's do something else. Let's study how does it diverge. Okay, it goes to infinity, that we know, but how does it go to infinity? Let's make a kind of an expansion. Not in L, but 1 over L. Because 1 over L will go to 0. So it's a small number, so we can make a Taylor expansion. This is equal to minus mu 0 over 4 pi I logarithm of, let me do this thing. I will take the numerator and the denominator under L over 2 parentheses. Logarithm of L over 2 of square root of 1 plus 4r squared over L squared minus 1 divided by L over 2 square root of 1 plus 4r squared over L squared plus 1. So L over 2's, they cancel. Well, yes. Where? Here. Now here there is a square root. I take L over 2 squared out of that square root and it gets out as L over 2. What remains is, well, 1 plus r squared. I took out the L squared over 4, so 4r squared over L squared. Minus 1, well, basically the same thing with a relative plus sign. Still not much improvement, basically because if you take the L goes to infinity limit, now this is 0, you have 1 minus 1, that is 0, over 2. Logarithm of 0 is infinite, yes. Yes, that is the tangent. But you see, what I did in the line over here, I get twice the logarithm of tangent. I wrote that as the logarithm of tangent squared. So that 2 disappeared, it moved to the power. I just didn't want to put another square root sign. Now will come the step that will save us, kind of. We know that at 1 plus x to the power n, if x is sufficiently small, this is nothing but 1 plus nx. So az partial is actually minus mu 0 over 4 pi I logarithm of 1 plus twice r squared over L squared minus 1 divided by 1 plus twice r squared over L squared plus 1. I'm assuming L is, I didn't really take the L goes to infinity limit yet, but it is close to infinity. It's huge compared to R, so this expansion will be sufficient for me. Well, these two cancel. This is equal to minus mu 0 over 4 pi I logarithm of minus 2 plus 2r squared over L squared plus logarithm of 2r squared over, let's say, L0 squared plus logarithm of L0 squared over L squared. What is L0? Well, kind of an arbitrary length. Just like in the case of in electrostatics, we chose an arbitrary point to set the electrostatic potential to 0, and this basically corresponds to a similar length. It is just arbitrary. In fact, we didn't yet, I mean, this expression doesn't even depend on L0 because here you have the minus the logarithm of L0 squared. Here you have the plus logarithm of L0 squared. L0 squared, they just cancel each other. Now, the reason why I introduced that L0 is you cannot really talk about the logarithm of 1 meter. The argument of the logarithm function has to be dimensionless. It cannot have a unit. There's no logarithm of 1 meter. So I introduced this L0 to make these ratios to be dimensionless. There's no unit dimension. Yes, but I need that L0 for the next step. Now let's assume we take the L go to infinity limit. If L goes to infinity, this is just 2. So we have logarithm minus the logarithm of 2, some number. Well, this is just some number, again. This diverges. So now we know why it diverges, AZ. There is this factor over there which will diverge when we take the limit L go to infinity. But look at that number. That is just a constant. A constant can always be written as the gradient of something. A constant in the z direction will be the gradient of that constant times z. But I can always add or subtract the gradient of any function from my vector potential. So I can just get rid of that, throw it away. This is constant, so I can throw it away. Because I can always add the gradient of any function to my vector potential. Well, if I throw it away, then now I can take my L go to infinity limit. AZ would be just mu0 over 4 pi I logarithm of 2 plus the logarithm of 2r squared over L0 squared. Or this is mu0 over 4 pi I times the logarithm of 4r squared over L0 squared. This is my AZ.
Partially?
No, I already took the limit. AZ is equal to limit as L goes to infinity of AZ partial minus the constant term the first line is my AZ partial. That constant term I can just throw it away. I will not get the same vector potential, but I will get a vector potential that describes the same magnetic field. So I just throw away the constant term. Now once I throw away the constant term that diverges, I can take the L goes to infinity limit. And when I take that limit, this is what I obtain for the vector potential. Constant in the sense of independent of the position at which I'm studying my B field. You see, when I'm taking the curl, I'm taking the derivatives with respect to the coordinates of the point at which I'm trying to evaluate B. Those are, let's say, x, y, and z. Well, that R depends on x, y. It doesn't depend on z. But L doesn't depend on x, y, or z. So in that sense, that is a constant term. Of course, it depends on L. As you change L, that's not a constant, but what I mean by constant is independent of x, y, or z. Well, I have this 2r squared over here. I have a logarithm of 2 over here. Sorry that I made a mistake there. This is a minus sign. So this is minus, and hence the result is L0 squared over r squared. Now we also have an interpretation of what this L0 is. R is equal to L0 is the point at which the vector potential is 0.
Elindeki
It's a constant, you're right. I can throw it away, I can add it. But it doesn't bother me in the sense that it is a finite number. It will not contribute to my derivatives. You see, L0 will not contribute to my derivatives also. We didn't take it to be 0. You see, J is Jz in the Z direction. There is only current running in this direction, which is the Z direction. J doesn't have a X or the Y component. So since J doesn't have an X or a Y component, Ax, which will be integral of Jx, will be 0. Ay, which is the integral of Jy, will be 0.
In the last formula, R is constant and L0 is also constant. So
No, R is not a constant. You see, assuming my wire is that X is equal to Y is equal to 0 point, then R, capital R, is equal to square root of X squared plus Y squared. It is the distance from the wire. Or this is equal to mu 0 over 4 pi I logarithm of L0 squared divided by X squared plus Y squared at the point R.
hocam şimdi R sonsuza gidince
R, why should R go to infinity? R is my observation point. I'm evaluating my vector potential at the point R. You see, R, or let me write it in this form. My position vector is R in the, let's say, S hat direction plus some Z in the Z hat direction. Or in terms of the Cartesian coordinates, R squared is equal to X squared plus Y squared. I'm trying to calculate the vector potential at that point. Of course, if you try to calculate the vector potential at infinity, then the vector potential at infinity is divergent. Just like in electrostatics. If you have an infinite wire, the potential at infinity is infinite if you choose another arbitrary point to have a zero potential.
Vektörü yani bu field manyetik olan field'ına şey mi oluyor? Dik mi oluyor?
A. Well, you see, the curl of A, is it perpendicular to A? Not, I would say not necessarily.
hocam biz şimdi şuna constant deyip attık ya. Ama aslında o L'ye bağlı ve L'ye göre türevini alınca
Well, I'm not taking the derivative with respect to L. I'm taking derivative with respect to X, Y, or Z. Not with respect to L. Shall we test that this indeed gives us the correct vector potential, correct magnetic field, just to make sure? In cylindrical coordinates, that's the easiest system I can use here. With AS, this is the radial part, is equal to 0, A phi. This is equal to 0, AZ. This is the only one that is non-zero. Curl of A will be in the S hat direction 1 over s derivative of az with respect to phi. In the phi hat direction, minus the derivative of vz with respect to s, plus in the z hat direction, 0. Well, az doesn't depend on phi, it only depends on, no, this is not v, this is a. This derivative is 0 because az is independent of phi. So this is equal to minus derivative of az, derivative with respect to s of mu 0 over 4 pi I logarithm of L0 squared over s squared. Minus mu 0 over 4 pi I times derivative with respect to s of minus 2 logarithm of s over L0 in the phi hat direction. This is equal to mu 0 over 2 pi I. If you take the derivative, that just gives you 1 over s in the phi hat direction. Mu 0 over 2 pi s times I in the phi hat direction. This is our B that we had already calculated. You see, if you go back, we already know that just use your right hand, your thumb in the direction of the current, your finger curls in the direction of B. So it is going around our wire. Well, this direction is our phi hat direction. Okay, so in the derivation, we just threw away some of the factors, but we justified that throwing away those factors because, I mean, eventually to calculate the magnetic field, we will take the derivatives of the components and the derivatives with respect to the coordinates of the point at which we are trying to evaluate. So any constant that doesn't depend on these coordinates will not contribute, like L. L doesn't depend on the coordinates of my point. So they will not contribute in these derivatives. So if I just throw them away, add them, it doesn't make any difference. As you see, in this derivative, L0 also doesn't make any difference. So if it was not for dimensional reasons, I could have just thrown away L0 as well. In the derivative, it has no contribution. The only reason why I keep L0 is that the logarithm of a dimension full quantity just doesn't have any meaning. To be formally correct, I keep L0 and any logarithm of two factors.
Peki hocam L0 burada nasıl göstereceğiz L0'yu?
Well, we will not. You don't need to show it. Well, you see, if you look at this point, L0 is the distance of the points from the wire, at which point AZ is 0. If we just set R is equal to L0, AZ is 0. The vector potential is 0 at that point. So it's the 0 of the vector potential. Instead of choosing infinity to be the 0 of our vector potential, we just choose L0 to be the 0 of our vector potential. Why shouldn't I? Well, you see, what we are actually saying is that the vector potential has to be finite, right? So we would like to work with finite quantities. We want to take their derivatives. We want to study its changes. If it is finite, I also know that I can always add or subtract a constant. In fact, I can always add or subtract a constant vector. So if you just, let's say at this point, the vector potential is, let's say, A0. Okay, I can subtract this A0 constant vector from my vector potential, and my new vector potential will be 0 at that point. So I can always choose an arbitrary point to have a 0 vector potential.
Şimdi hocam bizim bu vektör field bu wire'dan mı başlıyor yoksa ren bu noktadan mı başlıyor?
Let's draw our vector field. This is my wire. My vector potential is AZ in the Z direction. So these are my vector fields. Vector potentials. Well, let's say this has a distance L0.
Burada niye ters döndü hocam?
Let's see, if R is less than L0, look at this number. If R is less than L0, then this is a number larger than 1, logarithm of a number larger than 1 is positive, so AZ is positive. If R is larger than L0, then L0 squared over R squared is a number less than 1. Logarithm of a number less than 1 is negative. So AZ is negative, my vector potential is in the minus Z direction. So these are how the vector potential lines look like.
O zaman şimdi o noktaya kadar manyetik alan içeri doğru, o noktanın ötesine geçince dışarı doğru mu dönüyor manyetik alan?
Let's see. This is our magnetic field, B field. It is always in the phi hat direction. With the sign change of A doesn't necessarily correspond to a sign change in B. Because B is not proportional to A. B is proportional to the derivatives of A. So you see, if you have a function that goes like this, increasing all the time, its derivative will always be positive. The function itself can have negative values or positive values, but the derivative will always be positive. Other questions? Or another example.
Biraz yukarı geldi. Bu R noktası var ya hocam aşağıda.
Okay.
Hani A vektörü burada işte pozitif, burada negatif. Peki simetri var mı?
Sure. You see, this is actually a cylinder. If you just specify the distance from this wire, it's a cylinder. Inside this cylinder of radius L0, my vector potential is pointing upward. Outside this cylinder, it's pointing downward.
Burada da bir işten söz edebilir miyiz? Yani
No.
manyetik.
Magnetic field doesn't do any work. So A doesn't really correspond to any kind of energy or change in energy, unlike the electrostatic potential.
Yani hocam bu durumda manyetik alan bu vektör çizgileri için equipotential surface gibi.
Well, you see, these field lines doesn't really have much meaning. Like for we talked about equipotential surfaces because if you just say the function is constant, it specifies a surface. But specifying a vector is constant doesn't really have too much of a meaning. Let's do another example. Let's try to find the vector potential of the solenoid. If you remember, Did we study? Yeah, we studied the solenoid, right? Okay, so let's study the solenoid. And then we can find the vector potential corresponding to it. Well, a solenoid is basically, we have these wires, rings, let's say. One next to the other one, such that it traps the magnetic field lines inside. So let's say you have the, if you assume it to be infinite, it's wrapped with these wires which carry a current I. The magnetic field lines, let me just draw its cross section. So here the current is coming out. Here the current is going in. The magnetic field lines of this solenoid will be horizontal. This is our B. Outside, B will be 0. Well, basically, B has to form closed loops. So it just goes until infinity. At infinity, you can think of it as at infinity they are leaving the solenoid, but then at infinity, once they leave the solenoid, they will just spread out. And this point, which is infinite distance from that point at infinity, the density of magnetic field lines at this point will be 0. So the magnetic B field will be 0 here. Now let's calculate B inside. I will assume a cylindrical solenoid, so it has this rotational symmetry. Let's say this is my z-axis. B field, at least its magnitude, well, it cannot depend on z. In general, it can depend on s, phi, and z. But it cannot depend on z because I have this translational symmetry. So if I just translate it along the solenoid, nothing changes. So it should be independent of z. Furthermore, if I rotate my solenoid around its axis, again nothing changes. So the magnitude should also be independent of phi coordinate. So it can only depend on the distance from the central axis, if at all. We don't know whether it depends, but at most it can depend on that one. Furthermore, I know that B is in the z direction. Now BS in the z direction. Well, I don't know whether it's in the positive z or my negative z direction, let's say, in this graph, although I plotted it assuming it's in the plus z direction. Well, we can drive it. We can actually show it. If BS turns out to be positive, then B is in the positive z direction. If BS turns out to be negative, then it will be in the minus z direction. We can use the Ampere's law. B dot dl over any closed loop should be equal to mu 0 times the total enclosed current. So I just need to choose a suitable loop to evaluate this B dot dl integral. So let me choose this loop. In this direction. Let's call this A, B, C, and D points. So B dot dl around this loop is the integral of B dot dl from A to B plus B dot dl from B to C plus B dot dl from C to D plus B dot dl from D to A. Now from A to B, dl is pointing in that direction. B is, in this part of that segment, B is 0. In the other part, B is in this direction, this is my DL, this is B, their scalar product is 0. So B dot DL as I go from A to B is 0 either because B is 0 or because B dot DL, B is perpendicular to DL. So this is 0. Well, the same holds for C to D. As I go from C to D, my DL vectors are in this direction. B is either 0 or pointing in this, or perpendicular to DL. So the integral from C to D is also 0. From D to A, I'm integrating over this line, but in this, along this line, B is 0. So this is 0. So the only remaining part is the integral from B to C, and from B to C, the L vector is nothing but the L in the Z direction. So this integral becomes BS times DL from B to C. Let me call this length L. Well, BS is constant. S is constant from B to C. Remember, S is the distance from the center of the solenoid. And B to C line is parallel to the axis of the solenoid. So S is constant. I can take it out. The remaining integral is nothing but L. Now let us assume that there are, this should be equal to mu0 times I enclosed. Let me assume that there are n wires running in my loop in this segment L. Yeah, you see I have 1, 2, 3, 4, 5, up to n of them. So the total current running through my area, total enclosed current, would be just n times I plus or minus Well, to determine the positive direction of the current, again, take your right hand, wrap your fingers in the direction of the loop. The loop is going like this, so wrap your fingers. So this is the positive direction of the current. All the currents are running in the positive direction. So it is just mu0 n times I. This is the total enclosed current. And hence, Bs is equal to mu0 times n over L I. It turned out to be independent of S also. It doesn't depend on my distance from the central axis of the wire, central axis of the solenoid. So let us just call N. It's the number of turns per unit length. So BSB, S is equal to mu0 Ni. Or B as a function of my position, this will be equal to mu0 Ni if S is less than the radius of the solenoid, and 0 if S is larger than R. Now, the next thing that we need to, well, of course, in the Z direction. The next thing we have to figure out is what is the vector potential corresponding to this thing. Okay, one thing to note from our previous example, you see in the previous example we have the current running in this direction. And the vector potential also turned out to be running in the same direction. Well, in this problem, I will make the assumption that my current is running in the phi hat direction. So I will assume that my vector potential is also running in the phi hat direction. It's running in the phi hat direction. Well, I have translational symmetry, so it cannot depend, translation along the z, it cannot depend on z. I have rotational symmetry, so it also cannot depend on phi. The only thing, this component in the phi direction is that it can depend on s. Well, this is an assumption. I didn't derive it. But you see, there are infinitely many vector potentials that we can find. If we can just find one of them, that's enough for us. So I'm just looking for whether there is a vector potential that satisfies this condition. Well, let's write the curl of this A in cylindrical coordinates. Okay, just look up the expression for the curl, and this becomes the part that contains the phi component derivative of A with respect to Z in the S hat direction and 0 in the phi hat direction plus 1 over S derivative with respect to S of S times A minus derivative of A, no, that's it. This is in the Z direction. Well, A doesn't depend on Z, so this term is also 0. So this is equal to 1 over S, well, sorry, this is not R, but S, derivative with respect to S times A in the Z hat direction. But we know what this should be. This should be equal to mu0 n times I Z hat times 1 if S is less than R, 0 if S is larger than R. Now we need to solve this equation. Okay, that we will do on Friday. Any questions before you go? Before they kick us out?
There's no recitation tomorrow.
Well, no request, just 2 students asked for a recitation tomorrow. The same 2 asking the recitations for all Wednesdays. And I'm assuming only one of them showing in my office asking questions. Okay, see you tomorrow. See you on Friday.